everyone. Welcome. My name is Leanne. I'm here to welcome you to the Iron and Steel Museum. Tonight we do have a very special presentation about a 100-year-old piece of technology. It's my pleasure tonight to introduce you to Richard Smith Jr., who is our speaker, and he is the Manager Process and Product Design for ArcelorMittal Coatesville. So he is a present employee there. He is a professional engineer, and he began his career at Lukens Steel Company in 1977 and currently has more than 40 years of service at the Coatesville Steel site as well. He has completed extensive research about the American iron and steel industry, so you'll probably hear and see some of that tonight. And he has also authored various papers that I'm sure he would love to tell you about if you do have questions about those. As I said, tonight Rich will speak about a very special piece of technology. It is called a 206-inch rolling mill. So you'll learn about that tonight, and it has celebrated 100 years of operations this past May specifically. So it's a very special feat and accomplishment there. The 206-inch rolling mill was once crowned the world's largest plate mill, a title that it held for decades, for more than 40 years. So Rich will speak about a little bit about the history of rolling in Coatesville, the construction of the mill, and the challenges that the people here overcame to create the mill, and also about some of the special products that are made or were made with steel that was rolled on the 206-inch rolling mill. So please join me in welcoming Rich Smith.
Thank you, Leanne. It's great to talk to you this evening about something that's near and dear to my heart. I grew up in Coatesville, not very far from here, and I like to tell people I grew up in the shadows of the Lukens open hearth. This is a picture. Can you see on this side, or am I blocking you?
Can't see a little bit, but it's all right. That's all right. You got it.
If you had a remote, I could move around, but this is a shot of the Lukens Open Hearth shops number 2 and 3, taken around 1960. And that's the house I grew up in. So when I say I grew up in the shadow of the open hearth, I'm not stretching the truth like I usually do too much. I used to sneak out from the basement. Don't tell my mother, she's sitting here. But we would tell her that we were playing in a basement, sneak out, crawl over a couple fences, get out to 30 and sneak into town, not at night because that would have aroused suspicion. But I remember crossing under one of these 2 bridges. There used to be 2 overpasses, and you would go under the bridge and you would see the big neon sign on the front of the open hearth proclaiming the world's largest plate mill. And all the trucks in Lukens that I would see going back and forth, they were gray with a big L on the door, and under the door it said world's largest plate mill. I had some relatives that worked in a mill, so I heard about this mill all the time. But let's start at the beginning. We know that Isaac Pennock was the founder of the mill that is now ArcelorMittal but became Lukens. And he started off in 1793 at a little place about 4 miles south of here, which he named the Federal Slitting Mill. In 1810, he expanded, kept the mill down south of Coatesville, and with a fellow named Jesse Kersey, bought a 110-acre farm from Kersey's father-in-law, Moses Coates, the man for whom Coatesville is named. And it had a small sawmill that was powered by the Brandywine, and they converted that into a slitting mill, and they named it the Brandywine Iron Works and Nail Factory. Pennock and Kersey ran that enterprise together for 6 years, and then Isaac bought out his partner. His daughter Rebecca had married a doctor from Philadelphia, and he turned the business over to his daughter and son-in-law in 1817. Dr. Lukens had been running the Federal Slitting Mill as he learned the iron business, and in 1817 him and Rebecca moved to Coatesville to run this Brandywine Iron Works. Dr. Lukens was an educated man, and he saw an opportunity in the boilerplate business, and the records say he modified his mill. What I think he did was widen the mill to roll plates, and in 1818, just 100 years ago, or 200 years ago, he produced the first boilerplate rolled in America for the fireboxes of steamboats. Robert Fulton and others were developing steamboats, The original boilers were made out of copper. That was too expensive, so they looked for iron boilerplate quality, and they couldn't find it in America. They were importing it from England. That got to be too expensive, and Dr. Lukens stepped in and thought he could make a go of it, and he did. We don't know the exact size of the mill back then, but the records show that in this time period, he produced plates that were 25 to 30 inches wide, so we believe the mill was around 36 inches wide. This is what an early Colonial rolling and slitting mill looked like. It had a small furnace to heat bars that came from the forge. It had a very narrow rolling mill that would roll those bars out, and then it had a slitting mill that would cut them to various widths. It could also cut them to nail rods. This is a table that they would use to bundle the nail rods. Slitting mill looked like this. It had two rolls, the top and the bottom, and a lot of disc on one and grooves in the upper roll, and the disc and the grooves fit together and would shear the plate or cut the sides of it to various widths. And they could go down to 1/4 by 1/4, 1/2 by 1/2, 3/4 by 3/4 for nail rods, or make bars for flat stock that were 2, 3, 4 inches wide. Since these were all powered by water wheels, and water only flows in one direction, the water wheel turned one of the rolls in one direction, but rolls turn in opposite directions, so it had to have some gearing to transmit the direction of rotation in the opposite sense to turn the top roll. And just when things were going fairly well, Dr. Lukens died from a fever in 1825. Even though he was a doctor before penicillin, getting a fever could be a lethal encounter. On his deathbed, he asked Rebecca to promise to carry on the business. She did, and in doing so, became the first woman industrial leader in America. She rebuilt the mill in 1834. You have to remember that these mills back then were not anchored in concrete. They would dig a pit and use heavy timbers, cribbed or crisscross, up out of the hole and bolt the mill or the housings to these timbers. Being in the ground, after a few years, they would start to rot, and the mill would get a little loose on its moorings, so every so many years they would have to rebuild the mill. Rebecca rebuilt it in 1834, and we know that she took it out to 48 inches. Now, to drive a longer roll with bigger diameter rolls, you needed more power, so she built a new dam that was higher. Water power works by kinetic energy. The bigger the difference between the top of the dam and the application of the power gives you more rotational ability. So she raised the height of the dam to create a greater fall and give more power to the rolls. She ran a business until 1847, when she retired and turned the active operation of the business over to the two men who married her daughters, Abram Gibbons, who came into the business in 1842, and another doctor, Charles Huston, who came into the business in 1849. Abram eventually left and started the first bank in Coatesville, but Dr. Charles Huston became an ironmaster like his father-in-law. Dr. Huston made the last renovations to the water-powered mill in 1853. Again, he installed a larger water wheel with new, bigger, and better gearing and a heavy flywheel to convey more power to the rolls. And he widened it from 48 inches to 66 inches and increased the diameter of the rolls to 21 inches. The mills back in those days were housed in a barn-like structure, and they typically had 10 men on a crew. Here they had expanded a little bit. They had a building, couple additions to the building, and a picture was taken around 1870 or so, and they have about 20 or 25 people employed at the time. Now we know what Dr. Huston's mill looks like because it appears that sometime around 1920 they took the mill and moved it to the other side of the Brandywine and put it in an old building. You can see the flywheel inside the building. The water wheel turned a shaft, and all the power came from the shaft. If you installed a flywheel, the flywheel would turn. Once it got up to speed and was spinning, it stored power. So if the water flow decreased a little bit, or if they took too big of a draft on the rolls and it started to bog down the water wheel, the energy stored in the flywheel would continue the rolls turning. In the old days, if they took too big of a draft and the mill rolls started to slow down, the men would have to run out and jump on a water wheel, and the additional weight would keep the thing turning and prevent the rolls from stalling on a hot piece and cracking the rolls. A flywheel is kind of like a gyroscope. Has anyone ever played with a gyroscope when they were a kid? They used to have little ones you put on a rope and you spin it, and once it got turning, it wouldn't fall over because it had so much energy stored in the rotation of it. So the flywheel was attached to the shaft. The shaft drove the bottom work roll. It had a shaft that went over to a gearbox. The gearbox was like a pinion stand that changed the direction of rotation for the upper shaft and then turned the upper roll. An interesting feature of this mill area is a raised platform where the foreman would stand and oversee the operations. And it was called a pulpit because it was kind of like a church pulpit where the podium was raised above the congregation, so the pastor could look directly into his congregation's eyes and tell who was paying attention to his sermon. This was called a pulpit, and it's interesting that even today, any operating enclosure or any operating control area in a mill is still called a pulpit. Here's a picture that is often referred to as the old mill or the original mill, and I have to take a little bit of exception to that because this has the flywheel inside the building. And we know that the flywheel was not installed until 1853, so this can't be the 1810 rolling mill. This has to be the picture of the 1853 and later mill. And I think this picture was taken at that time because Abram Gibbons left and started a bank in Coatesville. And back then, there was no federal bank, no government-issued currency. Each bank had to issue their own currency. His bank issued notes, and he had to put pictures on the notes, and this is one of the pictures that was on that currency. So I think he hired a painter or a photographer to take a picture of the current mill, and that's what he used on his currency. The early mills back then were called two-high. They had two rolls, one on top of each other, and the rolls only turned in one direction because water only flowed in one direction. The plate was rolled between the two rolls, and then it had to get back to the other side to take another pass to keep reducing the starting material in drafts or taking thinner and taking thickness off the piece to make it thinner and thinner. So the piece had to be passed back over the mill. The bottom of the roll turned in one direction, but the top of that roll turned in the other direction. So if you got the piece up to the top of the roll, it would help pull the plate back to the other side, and then you just had to tilt it up and give it a little shove, and it would go back to the other side. Here's a picture.
What was the increment of
thickness? I think that most of the places started with bars that were 3 or 4 inches in thickness and rolled them down to 1/4 inch or 3/16.
They do it in increments of?
Probably. Iron is pretty soft, so you could probably take 1/4 inch or 1/2 inch draft on each pass. So it probably took 7 or 8 passes to get it down to the gauge they were looking for. Now here's a picture of one of these old mills in operation. You had the roller and a helper on one side, and he had these devices that looked like a wrench with a long fork on the end that they could handle the plate, get the edge of it, and get some leverage on it and move it around. They would have to lift it up and feed it between the rolls, and the poor guys on the other side were called catchers. They would have to catch the plate, lift it up to the top of this top roll, and give it a push and let the roll rotation pull it back to the other side, and then drop it and put it through again. In the 1830s, steam locomotive came to America. The original locomotives were very small, but as trains start to crisscross the continent, the locomotives needed to be more powerful. The steam engines got bigger and bigger. They needed tremendous amounts of boiler plates. This was in addition to the steamboats on the Mississippi and the other rivers that also ate up a lot of boiler plates. So the market started to grow quite quickly. This isn't good. At that time, because of this growing market for boiler plates, a number of mills popped up right here in Coatesville. Isaac's original mill, the Federal Slitting Mill, just south of Coatesville, was started in 1793, and then he started the Brandywine Iron Works in 1810. Laurel Forge in Mortonville put in a plate mill in 1825. Samuel Hatfield had a grist mill in Waggingtown, and he added a rolling mill in 1836. Hibernia Forge, which had been in existence since about 1793, added a rolling mill in 1837. And Rebecca's mother, Martha, sold Rogeby after her husband died, and with the money started a mill a half a mile up the Brandywine called Callan Iron Works, which was run by her son and son-in-law. Her daughter married son of Moses Coates, Dr. Jesse Coates, and together they ran the Callan Iron Works. And then three brothers started the Viaduct Iron Works, which we know as Carlson's, across the street, and that was started in 1838. Then in 1847, these mills were all powered by the Brandywine. In 1847, the three people who owned the Triadelphia, which became the Viaduct Iron Works, sold their interest and built a new mill in Thorndale called the Thorndale Iron Works, and that was powered by steam. So that was the first mill that was not on the Brandywine. So by 1847, there were 8 rolling mills within 4 miles of here, all employed 8 to 12 men in the mill. If they made bars, they might have another 10 men. They were barn-like structures. They were not very big, and they made 200 to 400 tons a year, which wasn't a lot. And I believe that a lot of these mills were started because people who were running a grist mill in Waggingtown or forges nearby saw Rebecca making a profit doing this and figured, if a woman can do it, I can make money doing this. And I think that might have had some initiative into the rise of some of these other rolling mills. During the Civil War, all of these local mills made out quite well. According to the tax records, they grew, they prospered. Just about every one of them doubled in size, and they made a lot of money according to the amount of tax that they paid. Now, it's said that Dr. Huston was a Quaker, Rebecca and her family were Quakers, so they refused to make any material for the war effort. But when you think about it, if all the other mills are making material for the war effort, who's taking care of the consumers who need iron? So even if they weren't making iron plates or boiler plates for the war effort, there was plenty of business to be had, so they prospered also. Dr. Huston thought about putting in a new mill around 1865 to handle this increase in business, but like it's typical after a war, there was a recession and he held off. But in 1870, he pulled the trigger and he built a new mill that was the first steam mill at Lukens. It was 84 inches wide. It had 25-inch diameter rolls, and they entered the market for wide boat iron. Now, boat iron could be made from puddled iron. Boiler iron had to be made from wrought iron. That went from the blast furnace to the forge to the rolling mill. Puddled iron could be made in a reverberatory furnace. They put either cast iron or scraps from plates in a furnace. They heated it up, drove the carbon off of it, mixed it with a big iron rod, and made a ball that looked like a big thing of cotton candy on a stick. They would take that over to a hammer, pound out the impurities, and they could make bars out of that. But that wasn't good enough for boilerplate, but that was good enough for boat iron. And at the time, the center of the boat building industry was shifting from New England, where the first wooden boats were made. When you think about it, where did the early settlers land? At Plymouth Rock. Well, after 3 months on the ocean, the boat typically needed to be repaired. So the boat industry grew up in New England. But in the 1870s and 1880s, they were switching over from wooden ships to ironclad ships, and Pennsylvania was the center of the iron industry. So a number of shipyards sprouted up between Wilmington and Philadelphia along the Delaware River. Here's a picture of the mill building that housed the 84 mill. It was off the Brandywine because it was steam driven, and here's the original water-powered rolling mill. Dr. Huston was a partner with Charles Penrose, who was a relative of Rebecca. It was typical for people to only take in relatives in their business, especially Quakers. Penrose was a Quaker, although he fought in the Civil War, and he was a partner with Dr. Huston. He had two sons, Abram Francis and Charles Lukens Steel. Now here's where it gets interesting. Dr. Huston was a medical doctor. He was educated. He sent his two sons off to Haverford College. They came back and joined the firm in 1872 and 1875. So suddenly you had 3 college graduates working in the iron industry here. Penrose died in 1881, and the two brothers became partners with their father in the business. Also at that time, the industry was switching over from iron to steel. Henry Bessemer had invented the Bessemer furnace that was able to produce large amounts of steel very quickly for the first time, and people were starting to realize that steel had a lot higher strength, and boiler makers and shipbuilders were switching over to steel. When you try to roll steel in a 2-high mill, which was a lot higher strength, when it got cold from passing it over, back and forth, over and over again, it got too cold to roll, and it started to exert so much force on the rolls that the rolls started to break. To compensate for that, Lukens added a 3-high finishing mill in 1880. It was driven by the same steam engine, so they rolled on one mill or the other. They would take an ingot out of the furnace, break it down to 1 to 2 inches on the 2-high mill. It was still thick enough to retain a lot of heat, and then they had a little transfer buggy that moved from one mill to the other, and they would shift it over to the 3-high mill. 3-high mill could roll it faster in both directions. They could get it down to the final thickness without any damage to the mill. Now again, you had to get these plates, which were getting bigger and bigger, back over the top of the mill. And to do that, they had this device called a horse. It was basically a platform. The mill drove the piece out of the mill and up the rollers on this device. And then you had counterweights all throughout the mill. You didn't have cranes back then. You had counterweights that were connected by this brace to the horse, and once the piece went up the ramp, the counterweight would pick up the other end of the horse, even with the top roll, let it down. The back end was higher than the roll, so it was still tilted, and the piece would roll down, catch the top roll, roll across to the other side, be caught on a receiving horse, which would then drop it down and feed it back into the mill. They were trying to eliminate the manual labor because the plates were getting wider and wider and heavier. Now, the 3-high mill was invented by a guy named John Fritz at Johnstown, but John Fritz was born about 5 miles from here. Apprenticed at Norristown and then went out to Johnstown, was a stupendous mechanical engineer. There's actually an award named for him that's given out each year to supposedly the best engineer in America, called the Fritz Medal. Eventually, Bethlehem hired him away. He went to Bethlehem, built their rail mill, and became a director of Lehigh University. We have a Lehigh grad here in the audience, and donated the money for the big mechanical testing lab, the Fritz Laboratories at Lehigh. The three-high mill was pretty ingenious. Since the middle roll always turned in one direction, if you put a roll in the bottom of it, you could roll the plate in one direction between those two rolls. Let me see if I get this working. Then they had tables on either side of the mill with cylinders that could lift the tables up, and that fed the piece between the middle roll and the top roll, which was the top of the middle roll was turning in the opposite direction. So when you lifted up the tables and fed the plate in between those two rolls, you could roll it back in the opposite direction and take a reduction. So now you could take a reduction in both directions and keep the plate moving and avoid losing the temperature and the piece getting cold.
Again, around a quarter inch at a time.
No, now you're rolling steel, so it's harder than iron, and you would be early on you could take quarter inch or half inch drafts, but when you got down near gauge, Chris, you're probably taking 100,000s, 50,000s off toward the end. Now something else interesting was going on locally. There was an iron master, and I love this name, Shezbazar Worth. He owned the Viaduct and the Laurel Iron Works in Mortonville with a partner named U. Steel. U. Steel was rather famous locally. He's the one that was instrumental in forming a railroad that went from Wilmington to Birdsboro and then Reading, and was housed, headquartered here in Coatesville, the Wilmington and Northern Railroad. But he was an iron master also. Now, Shezbazar had two sons, and they just happened to be almost the exact age as the Huston brothers. One was named John Sharpless. The Sharpless came from Shezbazar's wife. She was a Sharpless from Westchester. You may be familiar with that name. And they were Quakers. The other son was named William Penworth. They went off to Swarthmore College. They came back about the same time the Huston brothers did, and they entered the business with the father. So now you had four young college-educated guys in town looking to expand their business. The father died in 1874, and they became partners with U. Steel. But after a few years, they got the itch to go out on their own. They sold their interest to U in 1880, and they established the Brandywine Rolling Mill in 1881. This was located along the Brandywine for the power, and it was south of Lukens, where South Coatesville is now, right around Newlandville Road. Started up with a 90-inch wide mill, a little bit wider than the mill Lukens had, with a little bit bigger rolls. It was a two-high mill, had 28-inch diameter rolls, and started up in February of '92. And right between these two iron works was a company called Coatesville Boiler Works. They owned a lot of land between Lukens on the north and Worth Brothers or Brandywine Iron Works originally on the south. I found a pamphlet from Coatesville Boiler Works that was put out in 1900 or so, and in it they said that they settled on starting their business in Coatesville because at the turn of the century, 1900, there were 3,000 tons of plate rolled a day in Coatesville. Today, we roll about what, 7,000 tons a week? A week. So between all the mills in Coatesville, especially the Worth brothers and the Huston brothers, There were 3,000 tons a day rolled. They made products like kilns to dry out products, ladles for the iron and steel industry, and tanks and pressure vessels. Now, one thing you'll notice about this was before welding, so everything had to be fabricated with rivets. You would overlap two plates, and then you had to drill or punch a whole lot of holes to keep the parts together, heat up rivets, drive them through the holes, pound out the back of it. So that was extremely labor intensive. If you look at this tank, it's made of 3 layers or 3 tiers of plate. If you could roll a wider plate, half again as wide as these plates, you could make that tank out of 2 rows instead of 3 rows, and you would eliminate an entire row of rivets with all the work associated with mating those surfaces and connecting them. So that was the impetus for wider and wider rolling mills. Now, the salesman wanted Dr. Huston to widen his mill, but he didn't have much of incentive because the Valley Iron Works that Rebecca's mother had started were now owned and operated by 2 Pennock brothers, Charles and Joseph, and they were related to Isaac Pennock. Isaac's brother had sons, and these were the grandchildren of Isaac's brother. As I mentioned before, they were located on a Brandywine just about half a mile up the road, and early on they had 2 72-inch wide mills, and during the Civil War they installed an 86-inch wide 2-high mill. They rolled boiler and ship plates, and one of their claims to fame was that they had supplied plates for a steamship called the City of Peking, built by a shipyard in Chester in 1874. And at the time, it was the largest American steamship ever floated and second in the world. By the mid-1880s, Valley Iron was operating 4 rolling mills, including one that was 96 inches wide and one that was 110 inches wide. And that was reported to be the widest in the state of Pennsylvania. Pennsylvania was the center of the iron and steel industry, probably had 60 to 70% of all the rolling mills in the country. They were Quakers and relatives of Dr. Huston's wife. So they had a sweet deal going between them. Anytime Dr. Huston received an order for plates wider than he could roll on his 84-inch mill, the Pennocks rolled it for him, shipped it down, and he shipped it out to the customers. So he didn't have a very big incentive to increase the size of his mill. This is a picture of Valley Iron. This is looking south from about the bypass. It was bigger than Dr. Huston's mill, 3 big buildings that were longer than his. And this was the Iron Master's house. You can still see this if you come down 82 from the bypass, halfway between the bypass and Business 30. The bypass cuts across that hill right about this level, and you can just see the roof of this house. Both sets of brothers divided the roles in the industry between them. Abram Huston and William Worth handled the sales and marketing, and they became well known throughout the iron and steel industry because they participated in gatherings of all the steel companies. The brothers, Charles Huston and John Worth, focused on operating the mill. They became very skilled mechanical operators. And during the decade of the 80s, they focused on improving the efficiencies of their mills. They came up with innovative devices that made their mills work better, and both of them obtained patents for their innovations and improvements. At the same time, there were changes going on in the iron industry. People were fading out, going past iron and moving into steel because of the higher strength and the availability. People were putting in open hearths now, and steel became easier to obtain. This increased the demand for wider plates both for boilers and for ships because it reduced the number of seams required. And seams were places where failures occurred. You had a bunch of holes in the plate, you put the device under a lot of pressure in a steam boiler or locomotive. There was expansion and contraction, and eventually the rivets would work loose and the pressure vessel would start to leak. So the fewer seams you had, the longer life you would get out of your device. As people were transitioning to steel, the Valley iron mills were old and smaller, and they weren't powerful enough to roll steel. One of the brothers, Joseph Pennock, suddenly died in 1887 unexpectedly. He was the financial guy in the partnership. He had made some deals and took on some debt that the other partner couldn't handle, and within 2 months the place closed down, put all the men out of work. So Lukens lost its source of plates wider than 84 inches. Now they may have widened the 84 as early as 1880s. At some point the 84 was widened and eventually got out to 98 inches. Charles Lukens Huston lived to be 94 years old. He died around 1950. And in the 30s and 40s, when Lukens started their plate news and then Lukens Life, they would interview him from time to time, and he would tell stories about the old days and the early days. And he often mentions that the mill was changed several times, each time improving it or each time making it wider, but there's no documentation. The Association of Iron Makers, which became AISI, used to put out directories every 2 years, and the description of the mills never changed. It was always listed as 84 inches. But there were companies that went around and made maps of areas for insurance purposes, and in the 1880s they show, or in the 1890s, they show Lukens having a 120-inch mill and a 98-inch mill. So that's how I know this mill was widened, but I'm not sure exactly when. But to compensate for these things going on, under the direction of Charles Lukens Huston, the company built a 120-inch wide 3-high mill in 1890. It had bigger diameter rolls to handle the wider material. It was designed for wide boiler plate made out of steel. It was steam driven, started up on July 2nd, 1890, which happened to be the company's 80th anniversary. And now this mill could produce 40,000 tons a year. So Lukens went from a small player in the local area, only making a fifth of the total tonnage, to making half of the total tonnage coming out of Coatesville. Worth Brothers didn't sit still for that. In 1896, they built a mill that was 132 inches wide, a foot wider than the Lukens mill. Had obviously bigger diameter rolls. It was a 3-high. The middle roll was 22 inches in diameter. It only had a capacity of 40,000 tons because it didn't have the tables to take the plates away from the mill. And they took the title back as the widest plate mill in the country. Lukens didn't like that. The Huston brothers didn't sit still. They took their 120-inch mill out to 134 inches in 1900. They took out the rolls that were 34 inches in diameter, made them bigger, 36 to handle the wider width, put in some tables to take the plates away from the mill, reduce the manual labor, and they had a capacity of 90,000 tons a year. They reclaimed the title for a small time until a 136-inch mill was built somewhere else in Pennsylvania. In the meantime, Lukens was growing, and Charles Huston was using his knowledge to design and build a couple other mills. In 1900, they built a 48-inch universal mill. This was also driven by steam power. It had a good-sized roll for a narrow mill, 28-inch top and bottom, 21-inch center. You see a man standing here for size comparison. It was a pretty big mill, and you can see the gears here that change the direction of rotation to drive the rolls in opposite directions. This mill was especially built for rolling long, thin plates for beams. They didn't have beam mills back then. They would take long plates and fabricate 2 webs and a flange, rivet them together. It had vertical rolls on either side of the mill to keep the plate straight and make the edges nice that they could rivet them and fabricate these beams out of them. He also built a large slabbing mill in 1901. It was 108 inches wide. Here's a guy standing here. This is immense. It was built by Morgan Engineering in Ohio. It was designed by a mechanical engineer who was very famous at the time named Julian Kennedy. Lukens had hired him to do some work for them to improve the efficiency of their plant. Julian designed this for a Russian company, and for some reason they didn't take ownership of the mill, so Lukens bought it, and it was installed in a building that we now call the 84 Spares. It also had vertical rolls to control the width of the piece as it came through the mill. And then in 1903, Lukens built a 140-inch wide 3-high mill. Had 38-inch diameter rolls driven by a steam engine. And it not only had tables to take the plates away from the mill, but it had large cooling beds where the plates could cool. Up to this time, you took the plates, you stacked them up until they cooled. You picked them up, you took them to a shear to cut the sides and the ends to the size the customer ordered, and then you shipped them. Every time you handle a plate, it took time. Time was money. So they developed large cooling beds to keep the plates not only flat, but cooling them down and keeping them moving to the next operation. With a 140-inch mill, Lukens took back the title of the widest mill, and they held it for 2 months. The Worth brothers built a 152-inch 3-high mill with 42-inch diameter rolls, and it started up in August, 2 months after the 140 mill started. It didn't have nearly the capacity. You see, there's a picture. They took back the title and they used it in their advertising. Largest mill in America. They had the mill, table rolls that took the plate away, and then it stopped. And then you had to pick it up with a crane, move it over, put it in a pile, as opposed to cooling beds that move the plate right to the shears. 6 years later, a company in Cleveland, Ohio called Otis Steel also built a 152-inch mill with similar sized rolls as the Worth brothers. This was built by Morgan Engineering again, who built a slabbing mill, and this was an extremely powerful and heavy mill. It had a 3,000 horsepower steam engine to provide power, and it had a 100-ton flywheel that once you got that up and spinning, it stored a lot of energy. It rolled plates from 1/4 inch up to 1.5 inches. They had a 126-inch mill that was built in 1890, not too long after Lukens' 120-inch mill, and they replaced that mill with this 152-inch mill. Now, this mill was the heaviest mill built in the country up to that point. The total weight of all the castings that went together to build this mill approached 1,000 tons, and 6 of those castings weighed over 50 tons, including that big flywheel that's shown here in the circle. So they shared the title of the widest mill in the country with the Worth brothers. Eventually, they got out of the plate business. They built a hot strip mill, and that plant became a Jones & Laughlin, became an ISG plant, and now is part of ArcelorMittal. So today, this is one of our sister plants in Cleveland. Around the world, people are also building bigger mills. In Germany, they built a 165-inch wide 2-high mill. They didn't adopt the principle of the 3-high mill. They thought there was too much movement of the tables, so they stayed with reversing 2-high mills. This mill had 43-inch diameter rolls and was driven by an electric motor, not steam. It was built for rolling copper plates, which aren't nearly as strong as steel plates, and it started up in January of 1910. It was used for steel from 1948 after the war up until 1984, and then switched back to non-ferrous, copper, and softer materials. I went to a plate seminar in England in 2006 and met a couple people from Germany and England who were into the history of rolling mills, and they had tracked down these mills, and in 2006 this mill was still operating. But the biggest mill in the world was a 178-inch two-high mill built in 1910 at the Witkiewicz Works in Czechoslovakia as part of the Austrian Empire. It had 49-inch diameter rolls, also powered by an electric motor, and it held the title of the world's widest plate mill. It was built for thick, heavy armor plates, rolled its first plate in August of 1910, and it was capable of rolling ingots that weighed over 100 tons, which is amazing. This mill was shut down in 2006, so it operated just 4 years shy of 100 years. So sometime after 1910, the Huston brothers considered building a mill that was 180 inches wide to regain that title of the world's widest plate mill. They knew they needed rolls larger than 42-inch diameter because that's what they were using in the 152-inch mill, and to take that mill out wider, you needed a stiffer roll, so they knew the diameter had to grow. According to their calculations, they figured it had to be 48 to 50 inches in diameter. They used chilled iron rolls back then because that gave a very good surface to the plates that were rolled and came in contact with them. But the roll manufacturers, when they discussed this with them, didn't want to sign up. They said there's no way they could make a roll that big. They were having a lot of trouble making the 52-inch diameter rolls for Worth Brothers and Otis Steel. Often they would crack from shrinkage cracks during the casting, and they weren't making a lot of money on those rolls. They didn't want any parts of a roll that was bigger in diameter and longer in length. So back in Coatesville, one of the Lukens engineers thought about a four-high mill. There had been a four-high mill built in the 1880s. Carnegie Steel at Homestead, who turned out to be a big competitor of Lukens in the 1900s, built a four-high mill to roll armor plates. It was designed by Julian Kennedy, but it was not successful. In a four-high mill, the two work rolls are driven. The backup rolls, or support rolls, turned by contact with the work rolls. When you have a piece in a mill and it's exerting a lot of force between the mills, it's putting a lot of pressure on the backups and they turn very easily. But the bottom roll, when there's no piece in the mill, can only be driven by the friction of the work roll turning, and it has to make contact and spin that bigger, heavier backup roll. Apparently, it didn't work. The work roll would turn, the backup roll did not turn, and it just wore flat spots on the backup roll, on the work roll. And when that work roll came in contact with the plate, it made an uneven surface, and that wasn't very good, so they stopped making plates on that mill and used it for a slabbing mill. A slabbing mill takes ingots, breaks them down to 4 to 6 inches, and then they heat them again and feed them to the plate mill. So instead of the plate mill spending a lot of time taking an ingot from 16 or 18 inches down to 1 or 2 inches, the slabbing mill works in an intermediate capacity and does a lot of that work for them, so you can make more plates. To get around this problem, Lukens designed a friction drive for the bottom backup roll. They put another drive shaft coming out of the gearbox to turn that bottom backup roll. But you couldn't have a direct drive because you have two cylinders that are different diameters. And you have to, if you're driving one of them, you have to, or both of them, you have to have a certain ratio of the cylinders so they travel at the same speed when they mate. Otherwise, you're going to get some bucking and carrying on and breaking gears. So they came up with a friction drive that when you start to get binding, the clutch would slip and it wouldn't break anything. So they took this idea to the mill builders, and according to Charles Lukens in one of the papers he published, some of the mill builders laughed at him with this concept, said it was ridiculous. But United Engineering and Foundry in Pittsburgh said, yeah, we'll help you with that. So they helped them complete the design. Now the model that's in here has this bottom shaft on it. You can actually see it when the rolls are turning. The two main spindles drive the work rolls, and the friction drive drives the bottom backup roll. Now, United Engineering built our Steckel mill at Conshohocken in the 1990s, and I was on a team that worked on the design of that. We would go to Pittsburgh every week to go over drawings, and at lunchtime I would sneak off into their library and go through their historical archives. We had a monthly newsletter called Lukens Life. They had one called The United Way. And I went back through the old issues and found their version of the story of the 206 mill. And they said that Charles Huston came into their offices and laid out this concept about building this gigantic mill. And they said, yes, we'll be happy to help you with that. And they were on board from the beginning. This is how a 4-high mill works. You have small diameter work rolls, and to prevent those rolls from deflecting under load, you have much bigger backup rolls that provide support. That reduces the deflection, so you get a nice even thickness all the way across the width of the plate. If you get deflection, the center of the plate will be heavier to account for the deflection, and the thickness will decrease as you get out to the edges. 4-high mills roll in both directions. There's no tables to lift up, so there's less maintenance, and you can roll a plate very efficiently. The Huston brothers originally were considering a 180-inch mill, but they figured with this 4-high design, they could go a lot wider than 180 inches. So, according to some of the lore, Charles Huston called in his engineers and said, go out, measure rail cars, check the tracks, find out the clearances, see if there are any restrictions for tunnels and bridges, and tell me what the widest plate is that I can ship. They came back and said 15-foot or 180-inch wide plates could be shipped by rail, but if you could get them to the shipyards, there were no restrictions on how big of a plate you could stick in a boat or a barge and ship by water. And there were 2 ports close by, Wilmington, 35 miles to the south, Philadelphia, 40 miles to the east. So they decided to build a 17-foot wide mill, which is 204 inches, and they were going to roll 16-foot plates, which are 192 inches wide. They figured if, with special blocking, putting the plate in a rail car at an angle, and especially if you had well-bottom cars where the inside of the gondola dropped down between the wheels or the trucks and got closer to the tracks, typically railroad wheels are about that high, 2 or 3 foot in diameter, and the gondola sits on top of them. But if you take advantage of that space in between the wheels, you could set a plate down in there at an angle, and you could actually ship a 17-foot plate. To get around these concerns of the roll manufacturers, they determined that the work rolls could be as small as 34-inch diameter, and instead of 42-inch, using that extra material to take the rolls out to over 200 inches, and they could be made without the risk of breaking. But the backup rolls, which had to be bigger, could be cast out of steel. They could use steel and not the chilled iron. The chilled iron was for the surface of the plate. The backup rolls don't touch the surface, so they could be made out of cast steel. But they needed a roll grinder to dress these rolls when they came out of the mill. So they had to find someone who could build a lathe that was 4 foot bigger than the biggest one that had ever been built. And Norton Company in New England built the largest roll grinder that had been built up to that time. Here's a picture of the backup roll in the foundry. You can see how big it is. And the finished work rolls, polished up and ready to be shipped in Mesta's machine shop in Homestead outside of Pittsburgh. Next challenge was the mill housings. How are you going to get a mill housing big enough to take the forces that rolling was going to generate? They designed them out of steel instead of cast iron for the increased strength. But the housings with these 4 rolls stacked up were over 40 foot tall, and that far exceeded the capacity of anyone in the country to cast, let alone machine or ship something that big. They got around that by designing the housings in 4 parts, 2 side pieces, a top and a bottom piece to connect them all together. Here's pictures of the parts in the foundry, a side piece. Here's a man standing. You can get a feel for how big this is. And this is one of the top pieces. That way, these pieces were big enough to be transported from the foundry to the machine shop and here to Coatesville to be erected. Next challenge was the drive power. How are you going to turn these rolls? They considered an electric motor, which electrics were pretty much in the infancy in the early 1900s, but that would have required two motors of 12,000 horsepower each, plus all the equipment to generate the power. So they opted for a steam engine. Steam engine was a simpler installation. It reversed faster than electric motors, and the steam engine they installed could develop 25,000 horsepower. And it was also built by Mesta, who started out building steam engines and eventually got into building mills. They built a 140-inch mill that we operate in Coatesville today. After the plates are rolled, they may be out of flat, and you need a straightener to level out the plates or make them nice and flat. The 140 straightener had been built by a company in Wilmington. They went to them, and they designed a straightener. It was 210 inches wide, by far the biggest one ever built. Then they figured, how are you going to cool these plates after you roll them? They designed a chain-driven cooling bed that was 105 foot wide. It could take a plate 105 foot long. But if you rolled shorter plates, you don't want to use up all that space. So the cooling bed was divided up into three sections that worked independently. If you rolled a plate that was 35 foot or less, you could line them up side by side. If it was between 35 and 70, you used two of the sections and could put a short plate next to it. Long plates took all three sections. They supported the plates until they were cold, and then at the other end, there was a device that hydraulically lifted up the plates so you could inspect the bottom of them without turning the plates over. Again, here's a man that you can get a sense for how big these lifting devices were. Then you had to cut the plates. So the shears to cut the plates were 210 inches wide. Again, here's a man for a reference. You see how immense these shears are? They were 4 feet wider than the previous biggest shears made in America. So it was a big jump to take all the auxiliary equipment from 152 inches up to 206 inches. They installed two shears that were similar, one for cutting the length of the plate and then another one for cutting the sides of the plate. Up to that time, all the side trimming was done manually. Men would turn the plates around side to side and feed them into a shear. They were going to roll big, heavy plates, and they didn't think men could turn them, so they devised a device that would pick the plate up, spin it around, feed it to the shear, cut one side, back it out, spin it around 180 degrees, and feed the other side back in. So the 204-inch wide mill rolled the first plate on May 22nd, 1918. 100 years and 7 months ago. It was the first successful four-high plate mill in the world. It took over 2 years to build. They signed a contract in 1915, started construction in 1916, expected to start it up late in 1917, but delays occurred and it didn't start up until May. It had a capacity of over 200,000 tons a year. Now, I mentioned 204, and we're talking about 206. So which is it, 204 inches or 206? You could ask the question, how wide is the 206-inch mill? And that's kind of like asking, who's buried in Grant's tomb? Or what color is the old gray mare? Originally, they were going to roll a 17-foot wide plate, which is 204 inches. And they put out press releases that said they were in the process of building this 204-inch mill. This one says 204-inch rolls of the world's largest plate mill now being built by Lukens Iron and Steel Company. The first work rolls that they used were 17 feet exactly, or 204 inches. But they knew that they could fit 206-inch rolls in there, and they weren't sure of how they would act against the backup. They thought they might crack at the ends. So they had a set 206 inches long made for trials. in 1919, the next year after startup, they put the longer rolls in. They used them. They didn't break, didn't cause any problems. So all the rolls they ordered after that were 206, and the 204-inch mill became the 206-inch mill. So now that you built the widest mill in the world, what are you going to do with it? Well, you're going to roll the widest, heaviest plates in the world. And what do they look like? They are very big. Here's a big, thick ingot starting the rolling process, and you roll thick plates. When they get down to the final thickness, they are immense. What do you use those for? Well, they put out enough press ahead of time so designers could get an idea of what was possible with plates this wide. Here's a one-piece locomotive firebox and the combustion chamber that was made from a single plate that was 3/8 of an inch thick, 195.5 inches wide, and 250 inches long. They took this plate, they cut it at this location and bent the plate around to make the smaller chamber and then fit a piece in here. So instead of having a lot of plates, made it up together and riveted, they were able to make this out of one piece, one plate with a little piece put in. This was designed by the superintendent of locomotive power that worked for the Pennsylvania Railroad. It was a very inventive design and significantly reduced the number of rivets in the fabrication of a locomotive firebox. Mesta, who supplied the rolls for us, used the products to make flywheels. Here's pictures of two different flywheels, one for an 18 horsepower drivetrain and the other for a 5,000 horsepower drivetrain. These were made out of a 7 3/4 inch thick plate that was 120 inch wide, and they cut the gears out of them and the flywheel so they got this mass without putting smaller plates together. Lukens made heads back then, both pressed and spun heads, big bowl type structures that were used to cap the ends of pressure vessels, locomotives, and tanks. They could make a plate 195 inches wide and then fabricate that into a bowl. An interesting side story, this head has a hole in it. They used to cut a hole and push a die through it to bend the corners, bend the edges up, and then weld something to that. When I was a kid, now Mom, you're not listening to this, they would ship these by rail and they would move them out onto the main line, and there was a siding up there. And we used to go up, crawl in the rail cars, run up inside these heads, grab the center, hold on, turn around, and slide down. It was the cheapest amusement ride around until the guards came and chased us away. These large heads are used for pressure vessels. Here's a gigantic, thick pressure vessel being transported. You see guys sitting on top here. Any idea what their job is? Wires. They have wooden poles, and when they come across the wire, their job was to lift it up so it didn't contact the metal head and electrocute someone. They were also used to cap pressure vessels. Here's one built by A.O. Smith, no relation, who you might know made a lot of water tanks in their day. They also made pressure vessels for refineries. They were also used for the hulls and bulkheads of submarines. At one time, every submarine made in America had the two ends made and fabricated here at Lukens. Now, little known story. A lot of people say that the 206 mill was the world champion for 40 years until U.S. Steel Gary built a 110-inch mill. But when I was a kid, I used to hear stories that after the war, America went into Japan to help with the reconstruction, and they found a mill that was wider than a 206 mill. There was one. In 1941, the Germans built a mill that was 5.3 meters wide, or 209 inches. It was powered by a steam engine, had 43-inch diameter work rolls and 63-inch diameter backup rolls, and it was 2 5/8 of an inch wider than the 206 mill. And like I mentioned, it remained a secret until after World War II. Now, this mill was built for rolling thick, heavy armor plates for the Japanese Navy. So naturally, they didn't want anyone to know about it. And the Germans weren't too forthcoming before World War II, so they weren't telling anyone either. This mill is capable of rolling ingots of weight over 150 tons. And as far as I know, this was still operating in 2008. I made a trip to Japan in 2000 and verified that this mill existed, and it was as wide as they said it was. After 30 years, the steam engine started to get worn out. So in 1948, they started to think about replacing the engine, and they decided it was time to electrify or put electric motors on it. That was a big job. They had to shut down the mill for 3 months to do this. Here's a picture of the foundations going in for the motor room. They poured over 900 cubic yards of concrete, about 300 in the ground as footings for this motor room. The steam engine was replaced with 2 4,000 horsepower electric motors. As I mentioned, the mill was shut down 3 months to remove the old equipment and put in the new equipment. The new motors were the largest mill motors ever made up to that point. The old drivetrain was cut up into pieces and charged into the open hearths, remelted, and the new electrical equipment was installed in the motor room. We've used that mill hard for a lot of years, and in 2013, 5 years ago, we figured it was time to give the old girl a rest, as they like to say in the steel business, and rehabilitate her. They tore the mill down completely, more than it had been taken apart in probably 50 or 60 years. Chris, you were part of that, weren't you? They replaced the top and bottom backup rolls. Here's a nice shiny new backup rolls. Again, here's 2 guys standing here. You get a sense for how big the rolls are. They replaced the window liners or the shims that make sure the rolls move up and down inside the frame evenly and smoothly. They put in new top and bottom work rolls. You see how many guys can stand in front of one of these? This is a backup roll. All right. Chris, are you in this picture?
No.
They voted you off the roll?
Yeah.
They also put in new work roll bearings. And finally, they put in new spindles or drive shafts that go between the motors and the rolls to drive those massive rolls. So they started up the mill. It was much stiffer, provided much more gauge uniformity across the width, and improved the flatness of the plates coming out of there. Just recently, we installed an optical device to measure the width of the plate. Up to this point, for almost 100 years, a guy would have to go out with a width stick, a long metal rod with a hook on the end. If the plate was supposed to be 160 inches wide, he would set it to around 162 or so to make sure he got it over the plate, and then try to judge how much gap he had between there. If it wasn't wide enough, if it was too wide, the little block wouldn't go down over, and that's about as accurate as you could measure. You see how hot it is? You don't want to spend a lot of time up close to that plate, so you might not get the best accuracy. This device sits way up in the rafters of the mill, looks down over the plate, and can measure the width and the length very quickly, very accurately, and saves time and temperature. And currently we have a big project going on to replace this 100-year-old straightener with a upgraded, very powerful leveler to help us do a better job making flat plates. So I'm proud to say that after 100 years, this mill has elected not to retire, not to take a buyout package, and it continues to work, although it's a reduced schedule. We only operated 8 to 12 hours a week because there's not that much call for plates wider than 160 inches. We have a 140-inch mill here in Coatesville. Our sister plant in Burns Harbor has a 160-inch wide mill. The 206 only rolls plates that are too heavy for those mills or too wide for those mills. So that can be done in 8 to 12 hours a week. But today that big mill, as they call it, is still important because there are Navy designs for aircraft carriers, surface ships, and submarines that have plates that are too wide or too heavy for any other mill in the country to make. We are the only plant, the only mill in the country that can make this armor. When Bethlehem bought us in 1998, one of their plans was to shut down the Sparrows Point mill and the Coatesville 206 mill. The Navy said, no, you're not going to do that. Bethlehem said, we are Bethlehem. You don't tell us what to do. The Navy said, we're the U.S. government, and we will tell you what to do. You will not shut down that mill. We are not going to redesign the aircraft carriers and the submarines. So we're proud to say that every aircraft carrier and every submarine in the fleet has plates that are rolled on a 2.6 mill here in Coatesville. Thank you for your attention. Any questions? Yes?
Do they still use the burlap bags and the salt to
They do not use salt. Salt is very corrosive. I said the backup rolls were originally designed to be turned into mills. There were stays and lands on the mill to use as turning, hold the turning devices to cut the backup rolls in the mill, and 75 years of throwing salt ate those away. So they stopped throwing salt. They still throw burlap, and they also use a fire hose to try to knock the scale off the surface. Yes?
Yes, yeah, I was just asking, I was talking to somebody today about the Burns Harbor.
Yes?
And they said it's totally shut down. Now, you're saying there is still operation there?
Burns Harbor is operating. Conshohocken rolling mill has shut down.
Yeah, I understood that. But I heard that, somebody told me that everything in Baltimore was
Baltimore?
Yeah.
Baltimore is shut down and leveled. Burns Harbor is out by Chicago.
Oh, there you go.
And that mill, that was the flagship mill of Bethlehem, and that is still operating.
So Baltimore's totally out.
Baltimore, Sparrows Point was built as Maryland Steel Company to roll rails for the railroads. When Charles Schwab bought them, he expanded them and they put in a universal mill. Midville bought Worth Brothers in 1915, and in 1923 Bethlehem bought Midville, which was the old Worth Brothers plant here in South Coatesville. At the time, there were 4 rolling mills in that plant. They took 2 of the rolling mills down to Sparrows Point and the head producing. The Worth Brothers competed with Lukens in everything, both plate and heads. Bethlehem took the flanging equipment down to Sparrows Point and took 2 of the plate mills down and began to roll plates at Sparrows Point. They took the 152-inch mill and widened it to 160 inches around 1932. In the 1950s, they added a 4-high finishing stand, and the 3-high mill became a breakdown mill for the 4-high finisher. In 1990 or so, I made a visit to Sparrows Point with Ed Fry and 2 other engineers from Lukens to look at their descaling system. We saw the 3-high mill operating. A millwright came up to me and said, "Hey, we have your old rolling mill." I said, "No, I don't think so." "No, we have your rolling mill." I said, "We never had a 160-inch wide mill." Back then, I kind of knew some history, but didn't know as much as I do today. I knew we had a 140-inch 3-high and a 2.6, and I was pretty sure we never had a 160. He was undeterred. He got some drawings and laid them out on the table, and in the title block it said Coatesville. He said, "See, I told you this was your mill." I said, "Whoa, I know there was other rolling mills in Coatesville. This must have came from one of the other rolling mills because we never had a 160. I eventually found out that that was the Worth Brothers mill, the 152 that Bethlehem took down and widened it out to 160.
I have a follow-up.
Yes.
Burns Harbor then is U.S. Steel, correct?
No,
Is it?
is ArcelorMittal.
No, I know.
Gary
Okay.
was U.S. Steel, and we now own a Gary mill. So it was always thought that the 2.6 mill was the widest mill until 1962, when U.S. Steel Gary built a 210-inch wide mill. Again, they had a 160 three-high mill that was built around 1900, and in the late 50s they thought about putting in a new mill. The Navy put in a quench and temper facility at Lukens to make armor plates in the 50s. We call it NAB, Navy Armor Building, because there were no steel mills that had quench and temper facilities to make armor. After World War II, during which all armors made in little fab shops, the government destroyed them all because that was the war to end all wars, and you were never going to need armor again. Then Korea came along, and suddenly they needed armor and no one could make it. So they funded the quench and temper line in Coatesville. That proved very successful, so Drever, who put in that line, started selling it to other companies. U.S. Steel bought a line that was about 160 inches wide and installed it in their plate mill. They were going to build a new four-high mill that was 160 wide. I think, again, just my personal belief, is that they said, why should we have a 160-inch wide mill? And that little place in Coatesville has the widest mill in the world. We're going to build a wider mill. So they made a mill that was convertible. It went from 160 to 210 inches wide. They would roll 160 3 weeks a month and then shut down. It took them 16 hours to take out the rolls, move the housings, put in bigger separators to connect the frames, put in the big rolls, and start rolling. They would roll wide plates for a week and then shut down for 16 more hours, move it back to 160. And they operated like that from 1962 to about 1992 when they automated their mill. And the French who automated our mill said, we had bad experience with loose mechanical components, pick a width and fix it. And they said, 160. They had a big water tank at their plate mill, and on the tank it said, world's widest plate mill. And around 1995, I was out there and I was teasing a guy. I said, hey, that's false advertising. Your mill's not 210 inches anymore. He said, yeah, we should change that. We should put world's best plate mill. I said, whoa, touche. And again, that Gary plate mill is now part of ArcelorMittal. We own this little island of a facility in the middle of a gigantic U.S. Steel plant. That mill is shut down, and we've brought some pieces of that mill to Coatesville to utilize. Yeah.
The Heritage Museum has acquired the buildings next to this office building. Are there any plans that some of this technology be housed at this new museum that they're planning back here?
This technology from the mill?
Well, or anything.
Well, we're still using the mill, so I
don't mean just transfer.
I hate to take pieces of Chris's mill and give them away, but I don't know. I haven't heard anything about that. You'd have to talk to some people at the plant to see. There might be some stuff available, spare parts that aren't going to be used anymore. Yes?
I have two questions. So if 206...
I'm having a special today, and I'll take 2 questions.
If 206 inches is your width, how long of something can you roll?
It depends on how big of a piece you start with. So we get the width, and then we get the thickness, and the length is determined by how much weight. So if you have a thick, wide plate, the biggest ingot we can make is 75 tons. And out of that, we can get about a 60-ton plate. And it's just a volume. You take that much weight, and the thicker it is, the shorter it's going to be at the same width. But if it's a narrow plate, it can get pretty long.
Okay, so I think that answers my second question. I wasn't sure if you are actually shaving it off or if it's flattening out.
It's compressing between two rolls. It squeezes the metal just like a rolling pin. You start with a big ball of dough. You push the pin down. You start rolling it out. The more force you put on it, the thinner the dough gets.
Okay, thank you.
Don't call me a dough boy. Yes.
Why would you convert a mill, go from 160 to 206? Why don't you just run the narrow width material on the 206 mill?
Because the 160 was stiffer, didn't get the flex in the rolls, and would make a light gauge plate better. Yes?
What do our friends in China have in the way of wide plate mills?
There are a lot of 5.5 meter mills, which is about 519 inches or 512 inches, something like that. They're used to make gas transmission pipelines that are like 90, 80 or 75 or 80 inch diameter pipe. At this seminar I went to in 2006, a guy gave a presentation that showed wide mills being built. And from 1970 until 1990, there were no wide mills built in the world. And then suddenly, everybody in India, Russia, and China started to build, and Japan started it, and then around 2000, it was China and India started to build these 5.5 meter wide mills to make this big pipe to get gas from Siberia down to the rest of Europe and Asia. So right now there's probably at least 10 5.5 meter wide mills. I also listened to a presentation from a mill builder that said, how wide could you go? Could you go to 240 inches? Could you go to 260 inches? And their conclusions were, if you could make a backup roll, you could make a mill that wide. It would have to be located right next to the shipyard because you're not going to transport them on a train or a truck. But if you build a steel mill next to a shipyard like they did in Korea, then you could make a wide mill and just move it right over to the shipyard. The trick is having foundries that can make the housings and the backup rolls. In the 80s, when there was a big recession in this country, a lot of steel mills went out of business, a lot of foundries that supplied parts went out of business. Around 2006 or so, another recession, more people went out of business. You can't cast a housing in this country big enough to make a mill today. You'd have to go to Europe to get the housings, and backup rolls are very hard to come by. Yes?
Why'd the Navy let us shut down Lukens, and who makes sonar spears for the Navy now?
That's a good question. I don't know who makes the sonar spheres. I think Combustion Engineering took that.
It's either combustion or CB&I.
CB&I. I think it was CB&I took that, and I don't. I know a guy that works with us was at CB&I, and they were getting plate. It might have been for sonar spheres, and they told him it came from Europe in a mill that had a press that would take an ingot and press it and then roll it. When we became part of ArcelorMittal, I made a trip over to see their mills with this guy, and we went to a big mill in France that was 132 inches wide, 140 some inches wide, built in the 30s, and we saw that mill that made the plates that took the business away from us. Now, they didn't fabricate them, but they provided the material for it.
I had heard for years that no one could hold the tolerances on those hole locations other than Lukens. A lot of other fabricators had tried to fabricate that when Lukens was doing it, and nobody could do it. All the big fabricators tried it.
Lukens was the first commercial weld shop in the United States.
Right.
They were instrumental in promoting welding and getting away from these rivets, but they also promoted making big things out of plate up to that point, to make a housing for something like a straightener that you saw here, they would take a lot of plates and put them together to make a big, thick housing. Lukens, or they would cast a housing. And Lukens was trying to get people to use plates instead of castings, so they did a lot of development work. I've seen pictures where they had strain gauges all over a structure where they would weld it, put these strain gauges on to show that they weren't going to have a lot of residual stresses or cracking, develop welding procedures, and then back in the day they made a lot of equipment for paper mills, big colanders and rollers. They used to ship lots of big parts out of Lukenwell. Dryer rolls, yep, for paper industry. Yes?
Yeah, the original mill housing was, I saw there where it was made in pieces, but it was welded together?
No, bolted together.
Okay, and when the mill was refurbished, were all those bolts replaced, or they were the original bolts?
Yeah.
No, I don't think we didn't disassemble the housing. They stripped everything down and all the wear parts. The housing is just a big frame that holds everything, and everything in there, closer you are to contact with the plate, the more wear you get, the more force, and that expands out, eventually gets to the housing, and the housing's like a big ring that stretches every time under load. They checked all the parts, but they didn't.
So those bolts were made back in, what, 1915 or 1916,
Yep.
and they're still being used today? Wow.
They're big bolts. I mean, they're not little bolts. They might be, I don't know, 8-10 inches in diameter.
Wow.
You know, the nut on there is probably 2 feet in diameter.
Takes 2 men and a boy to tighten it.
Yeah.
Any other questions?
A topic for a future is, I'm just so curious about where the material came from, how you got it here to the mills. It's not germane to tonight's, but that and a railroad to move it out of here, which had built these things.
Back in the day, or?
Yeah, more back in the day.
Yeah. That's interesting, yes, because I was telling Chris today, when they only had blast furnaces and then they would ship cast or pig iron to a forge and they would make bars. And in that picture of the mill from the 1870s, there was a donkey in that picture. And they actually, iron was soft and they would bend the bars in a U and strap them to the back of a donkey and move them to the plate mills. And these bars were only 3 by 5. Worth Brothers put in a mill. They were called muck mills because they took this puddled iron that wasn't so pure and they hammered it and then rolled it into a bar. And that's where the expression, I was down in the muck. Muck is considered mud, slime, dirt. They weren't as pure as wrought iron bars, and they would take a little bar that's 3 by 5 and try to make a plate out of it. And the one of the interviews, Charles Lukens said the early Mississippi steam plates for boilers were 1/4 inch thick and 27 inches wide. And for the flues, the exhaust, they were 49 inches long, and for the boilers, they were 72 inches long. So I calculated how much weight that is, and it's like 90 pounds and 132 pounds. And you figure a 3 by 5 bar only has to be about 50 inches long, but you're rolling that little bar in the short direction and trying to get it wider, or longer, and thinner. Because they didn't have steel, they didn't cast it into ingots. Any other questions? I appreciate you not falling asleep. I appreciate you asking questions. Now take out a piece of paper and a pen.
Well, I appreciate you recording this now, so we have it.
Recording. I wouldn't have said half the stuff. Okay, thank you.
Thank you.
Thank you.